So let's take a look at our first example of a chi-squared test of a single variance. So a college claims that their professors have a variance of their final exams is 88. A random sample of 24 professors from this college finds that their variance is 121. At alpha equals 0.05, is there significant evidence to claim that the college's variance is actually more than 88? So again, we're thinking variance, that's the square of standard deviation, so it gives us some type of spread of our data. Large variance means that we have a large variety of exam grades, but a small variance means that it's pretty close to one another. So it makes sense that a college might want to ask the question of how much variance do you have with your final exam grades. So we're doing hypothesis testing, so we're going to have our null hypothesis. We're going to do this based off of the college variance. So we're doing population variances, so we have sigma squared. And our null hypothesis says that that's going to be equal to 88. But our alternative says, wait a minute, what if instead this variance is larger than 88? We're trying to figure out, is it more than 88? So we have our null and our alternative hypothesis. Now here what we notice is that we have a one sample. Now notice, because we have a sample from a larger population, it's not distinct groups. If we think back to the other examples we did, there were different groups. So if we looked at the machine A, machine B example, we had two different groups we were testing between. Here we have the whole college and a sample of the 24 professors. So we have one sample and we're looking at standard deviation / variance. And so what this tells us is that we want to use a chi-squared test of one variance. So this was now one where we can't just simply plug things into the calculator and automatically have it calculate for us. We need to start to calculate things by hand. So our test statistic, we had the formula, chi-squared is equal to n minus 1 times s squared divided by sigma squared. So chi-squared, that's what we're calling this because we have a chi-squared distribution. So chi-squared is our test statistic, and we plug our numbers in. So n in this case is equal to 24. We have our s squared, this is the sample variance. Remember, s is the sample standard deviation, s squared is the sample variance, and that was going to be 121. Our sigma squared is the population variance, which is 88. So when we plug things in to our formula, we're going to get 23 times our 121 divided by 88. So we'll turn on our calculator, 23 times 121 divided by 88. We see this test statistic now is equal to 31.625. So now our p-value, how we're going to have to calculate this. Now, what's important for us to know is that we actually do have this type of distribution that's called a chi-square distribution. This is going to give us some information about our test statistics. Now, our alternative hypothesis says that we are larger than 88. So what that means is that we want to say this is our test statistic. This area out here, we are larger than this. So this area out here is our p-value. And so this number right here, this is our test statistic. So we'd like to figure out, how do I calculate the area outside of this for a chi-square distribution? So the buttons you're going to press on the calculator is you're going to press the second button, and then vars, that button says vars, above it says distr, so that stands for distribution. So we're going to click some distributions. This has a bunch of different distributions. So this tells us we have our normal distribution. There's this called the inverse normal. We have our t-distribution. And we have a chi-square distribution. You could scroll down and see there's also like the F distribution that we've looked at. So you could do all of these by hand, or quote unquote by hand if you wanted to, but we're going to go up and choose the one that we need for this test, and that's going to be chi-squared CDF. So you always choose the chi-squared CDF button. Press enter. And now when we choose our chi-squared CDF, the numbers that we're going to plug in is we're going to put in our lower bound. We're going to put in an upper bound. And then we're going to put in the degrees of freedom. So we have lower bound, upper bound, degrees of freedom. Now, if you remember, we said that the degrees of freedom is going to be n minus 1. So in this case, it's going to be 23. So into the calculator now, our lower bound is our test statistic. We're basically figuring out the lower bound is this number. And then the upper bound is going to be wherever we go to. So we're going to enter in 31.625. So we have 31.625. Put a comma. Then the upper bound is as large as we can get. So the largest that our calculator will work with is 10 to the 99. So we're going to enter in 10 raised to the 99. And then the degrees of freedom we said was going to be 23. So we enter in 23. Close the parentheses, press enter. And this is our p-value. So our p-value is going to be 0.1082. So remember, p-value, that's this area, and that's the probability that we are as extreme or more extreme. So with having a 121 be our variance, we're obviously larger than 88. So if we're more extreme, that means we're going to be larger than that. So our p-value is 0.1082. So now we just make our final conclusions. So now that since the p-value is equal to 0.1082, which is larger than 0.05, which is alpha, we do not reject the null hypothesis. So we do not reject the null hypothesis. There is not sufficient evidence to believe the variance of final exams is larger than 88. So that's what the result of our test gives us. So again, remember, this one is very special. When we have to do our chi-square test of a single variance, we have to calculate the test statistic using this formula over here, and then calculate the p-value by using our chi-squared CDF.